I was walking my dog earlier today, and I looked up and I noticed the power lines in my neighborhood, and usually I think they're kind of an eyesore, but I was kind of struck with the metaphor of it because I was looking up and I saw the sun, and I saw the leaves of the trees, and I saw these power lines, and I was thinking about the light-dependent reactions that we talked about last time, where electrons move from one protein to another protein to another protein in the thylakoid membrane. And that is just like the stream of electrons that moves through an electrical circuit. And if you run an electric current through something like a motor or a pump, you can get it to turn on. And that is the same way that some of the proteins in the thylakoid membrane work as well. So let's dive back in and pick up where we left off last time. Last time we began talking about the light-dependent reactions, which begins with pigments in photosystem 2 capturing light energy, and then you get photolysis, where water molecules get broken, and then oxygen is produced, and then you get an electron transport chain across the thylakoid membrane, a stream of high-energy electrons being passed from protein to protein to protein to protein until they eventually end up on NADP reductase, and that high-energy electron gets placed onto the NADPH coenzyme, which will be used in the second phase of photosynthesis. But along the way, as we were passing that electron down the line, we were powering a pump called cytochrome B6F, and that was filling up the thylakoid with positive charges, hydrogen atoms that had no electron attached to them. So they're just protons floating around here, are being force-fed into the thylakoid, and it is building this positive charge. It's getting more and more and more and more positive, and you would think, oh my god, positive charges repel positive charges. How could you possibly get any more positive charges being pumped in there? But there's enough energy flowing through this electron transport chain to power this pump to keep putting more and more and more protons in there. And this is what I was getting at when I was talking about the power lines. I mean, a power line would be an AC circuit, whereas this is slightly more similar to a DC circuit because the electrons are all going in the same direction consistently. It's not a perfect one-to-one correspondence, but still, it's very, very similar. There is a single stream of electrons moving in one direction through this electron transport chain, just like through the wires if you had a simple battery set up, and it is flowing through this protein, cytochrome B6F, and that is being used to pump things against their electrochemical gradient into the thylakoid. I've said it before, and I'll say it again, proteins are not just chemicals, they are machines. Now, if that was the whole story, then hydrogens would just keep building up and building up and building up hydrogen ions, more and more and more, and since they're ions, they're charged, they don't cross the membrane easily, so they're kind of trapped inside, and it would eventually just burst open. It would just rupture. You would essentially be building a little bomb there inside of the chloroplast. That's not a good idea. We need to be doing this for a reason, so we need to let the hydrogens out at some point. And we do that through another protein machine called ATP synthase. ATP synthase shows up in photosynthesis, and ATP synthase shows up in cellular respiration as well, so you get double bang for your buck on memorizing this protein. So the hydrogen ions are allowed to leave the thylakoid through ATP synthase only. That's the only way they're allowed out. So there's a big stream. They're lining up to try to get out. They're flowing out. High pressure stream on their way out of ATP synthase. And it's with enough force that we can get some work done, as a matter of fact. And this is where ATP synthase really shows itself as a cool protein, because as it's allowing these hydrogen ions to fall back down their electrochemical gradient, and that process of letting them escape is called chemiosmosis. Chemiosmosis is allowing hydrogen ions to flow down their electrochemical gradient. As it's doing that, every time it lets them escape, the whole thing rotates like a big old crank. And what it's doing is it's cranking together one ADP molecule, adenosine diphosphate, and one inorganic phosphate molecule. So you take an ADP, plus a PI, inorganic phosphate. You link them together using this protein, and once you make that bond, that connection, you get ATP out of the process. Hence the name of this protein enzyme, ATP synthase. It's an enzyme that does what? It synthesizes. It's a synthase. Oh, great. What does it synthesize? ATP synthase. This is an enzyme that makes ATP. And it uses the power of chemiosmosis in order to fuel that production of ATP. So every time a hydrogen ion tries to escape from the thylakoid, ATP synthase allows that to happen, but it makes it do work in the process. And the work it makes it do is make an ATP, so it cranks one together. Early on in the Unit 3 videos, I talked about potential energy and how in a dam, we capture a whole bunch of water uphill. We put a dam there in order to hold it up there, and then we slowly allow that water out of the dam. And because that water is now under high pressure and we are allowing it out through a turbine, we're able to generate electricity from that, right? We can capture that energy in order to do work for us. The chloroplast is doing the same thing here. It is using ATP synthase to capture energy from the flow of hydrogen ions out of the thylakoid. So the ions are flowing back out into the stroma of the chloroplast, and the ATP synthase is there to make some energy currency of the cell along the way. So that is the last thing that happens in the light-dependent reaction. The conversion of a large amount of potential energy in the form of a strong electrochemical gradient by ATP synthase converting it into chemical potential energy instead. Little bit of review from Unit 2. When you have a membrane, and materials want to get from one side of the membrane to the other side of the membrane, but they can't cross on their own, and they need the help of a protein to allow them passage, what do we call that? That's facilitated diffusion, right? So if that's facilitated diffusion, why is this called chemiosmosis? Well, sometimes when we're teaching things, we simplify a little bit for clarity. But the reason is because hydrogen ions will find water molecules in an aqueous solution, and they will lock themselves onto them, and they will form what's called an H3O plus molecule, a hydronium ion. So it's essentially a water molecule with an additional proton attached to it. So that is what is actually flowing through ATP synthase, hence the osmosis part. So it's called chemiosmosis, the flowing of hydrogen ions down their electrochemical gradient through ATP synthase. What have we done so far in photosynthesis? We've made oxygen during photolysis. We have made NADPH with NADP reductase. That was the product of the electron transport chain in the thylakoid membrane. And now we've made ATP using chemiosmosis and ATP synthase. So those are the three products of the light-dependent reactions: oxygen, ATP, and NADPH. Now, oxygen's a waste product of photosynthesis. That's going to leave. We don't need that. We are interested in using the ATP and the NADPH now, but we don't get to use them yet. We get to use those products in the second phase of photosynthesis, which is the light-independent reactions, which I will begin talking about in the next video. But we have one more topic to address before we can close out the light-dependent reactions. Whenever you make ATP in metabolism, it's referred to as phosphorylation. That's actually the term for adding a phosphate group to anything. But when you make ATP, you're adding a phosphate group usually to an ADP molecule. So you'll hear phosphorylation whenever we're talking about making ATP, in addition to other processes as well. In this case, when we're making ATP, using the power of sunlight. That's where the energy to get all these ions into the thylakoid originally came from, was from the sunlight captured from the photosystems. That is called photophosphorylation. Okay, photophosphorylation is what we're doing. But there are two different flavors of photophosphorylation. There's cyclic photophosphorylation and non-cyclic photophosphorylation. So far, we have been talking about non-cyclic photophosphorylation. So, what is cyclic photophosphorylation? Okay, well, these terms don't actually refer to the making of ATP itself. They refer to the pathway that the electrons take in the electron transport chain. So the non-cyclic version that we've been talking about, the electrons follow a straight path from PS2 to PQ, cytochrome B6F, to PC, to photosystem 1, FD, NADP reductase, to NADPH, and then that gets carried off somewhere else. But sometimes the ratio of NADPH to ATP is too high. That is, we already have too much NADPH. Or another way to say that might be we already reduced all the NADP plus that we have available in this chloroplast. We don't have any more of this coenzyme, so we can't put this high energy electron on anything. There's nowhere for it to actually go, so we can't just keep passing these electrons down the chain. So instead, what the chloroplast will do, what the thylakoid membrane will do, is start playing this game of circular hot potato. It'll start doing cyclic photophosphorylation. And in this case, photosystem 1, once it recharges that high energy electron, it passes it through one of these mobile electron carriers back to cytochrome B6F, which then passes it back to photosystem 1, and then back to cytochrome, and then back to photosystem, and then back to cytochrome, and then back to photosystem. Incidentally, plastoquinone, PQ, ferredoxin, FD, plastocyanin, PC, these are just smaller molecules that are able to move a little bit more easily in the membrane for shuttling the high energy electron from one place to the other. You don't need to know more details about them than that. They are different from each other, but not in a way that's important to us in this unit for this class. Okay, so what benefit does the thylakoid get from just passing the electron around in a circle? Well, it keeps passing through cytochrome B6F, which is a pump, so that keeps getting energy and it keeps putting more and more hydrogen ions into the thylakoid. And what's the ultimate consequence of that? Well, that promotes chemiosmosis, and that eventually causes ATP synthase to crank out more ATP. So by continuously charging up the electron and giving it to this pump, we're getting more ATP out of this deal. And then photosystem 1 just keeps recharging it. So that's what cyclic photophosphorylation is all about. We don't have any more NAD plus to reduce, so we might as well use this bright sunlight to just keep cranking out more and more ATP, because you can always use more ATP. It's the energy currency of the cell. It's basically never a bad idea to have some excess ATP on hand. So that's what the thylakoid membrane does in that situation. So that is called cyclic photophosphorylation, whereas the normal process, which passes it in a straight line from photosystem 2 all the way down to NADPH, is called non-cyclic photophosphorylation. And now that we have our NADPH and we got our ATP, we can send those two energy-carrying coenzymes over to the light-independent reactions where we will pick up next time.